All right, you're asked to prepare a dihydrogen monohydrogen phosphate solution that has the same pH as human blood, 7.40. Did you figure out the ratio of the concentrations?
Yeah, yes I did.
All right.
But I don't understand one of the conversions.
All right. You know, it's the this is the acid H2PO4 minus. The base is HPO4 2 minus. The pKa for the acid, this one I know, 7.20. Then the pH is equal to the pKa plus the log of the base. The acid ratio. And so part A is just what is the ratio that we
I
need.
get the part, but I don't get part B.
All right, what did you get for part A?
1.6.
Okay. Do you have more sig figs?
1.58.
1.58 was it?
Yeah.
1.58 doesn't round to, does it round? You only got to 2 sig figs?
Yeah.
1.58 what?
Is it, that's the best you've ever
Okay,
did.
all right, we'll just leave it 1.58. Okay, B. B. Suppose you have to prepare 1.00 liters of solution described in part A. 1.584? 48. That's not our final answer, so we'll carry extra digits. B. Suppose you have to prepare 1.00 liters of solution described in part A, and that this solution must be isotonic with blood, have the same osmotic pressure as blood. What masses of KH2PO4 and of Na2HPO4 12.12H2O would you use? Hint, refer to the definition of isotonic. Recall that a solution of sodium chloride with 9.2 grams sodium chloride per liter of solution is isotonic with blood, and assume that sodium chloride is completely ionized in aqueous solution. And so, isotonic, what was the definition of isotonic solution? Iso just means same, and tonic is just a solution, so it just means same concentration. But when we're dealing with the colligative properties, they depend on same concentration of solute particles. And so this isn't the total concentration. So for example, if we're looking at 0.100 molar acetic acid, it's not 0.100 moles of solute particles because some of the acetic acid is dissociated into ions. And so they're looking at the total molarity of solute particles in solution. And so they're saying a solution that's isotonic is 9.2 grams of sodium chloride per liter. And so we have 9.2 grams of sodium chloride per liter. Oftentimes solutions are written this way because it's easier. You just weigh it and then you dissolve it in a 1 liter volumetric flask. And so that the total volume is 1 liter. And this would be grams of sodium chloride per liter of water or per liter of solution. We have to figure that out. And so let me look here. It's per liter of solution, which would be different than liter of water. And so,
Wait, per liter solution, what does that mean? H2O or the buffer?
No, this is isotonic. And so this would be an isotonic saline. Or just salt solution. So if you want to make an isotonic saline, you take 9.2 grams of sodium chloride, get a 1 liter volumetric flask, and then fill it to the 1 liter mark. That would be an isotonic saline solution. Well, what we want is, okay, that's how many grams. That's just a matter of convenience, because if we had this in terms of molarity, Or if we had this in terms of molality, it's less convenient, you know, because you have to do a calculation. Here you just weigh it out, and so it's very straightforward. And so one of the solutions from our lab was given in this, grams per liter. That was grams of CbCl per liter of solution. The other, with the sodium hydroxide, was given in molarity. And so what we have to do is, we need to find out, because these are molar concentrations, we need to find out the molarity of the solute particles. Right, and so molarity of solute, but we don't have that conversion factor, moles per grams, except for sodium chloride. Yeah, we do.
Why do you want a molarity of solute?
Either that or we convert this into grams per liter. Which one do you want to do? You want to go here, grams to liter? But you know, grams per liter, they don't match up, because this is talking about the concentration of solute particles, not the grams of solute particles. And so if we were to convert this into grams per liter, that would be a complete waste of time, because we got to go back anyway, you know. Because just because we have 9.2 grams of sodium chloride doesn't mean we're going to have 9.2 grams of these salts. Not at all. It means that this was weighed like this just for a matter of convenience, to make the mixing of the solution easy, but not, you know, the chemistry of it.
Okay, but what's the solute particle?
The solute particles are the number of solute particles. The number is going to be huge, so we use moles to describe the number of solute particles rather than the actual number. As you recall, the colligative properties depend on how many solute particles are in solution, and so those are susceptible to deviations from ideal behavior. Therefore, we need to either compensate for those, ignore them. And so what do? We ignore them. We're going to say things behave ideally. When things behave ideally, did you guys take a look back at that chapter? (13). Chapter 13, page 587, this little table here, table 13.3, which shows sodium chloride. What's all those numbers next to sodium chloride mean? What is this showing? Summarize this table in two statements.
I don't think anybody has chapter 13.
Oh, I know. You all have, but you all have it from Chem 1A, right?
Good point, John. Good point. Or anyone who's made it.
But this is something I asked you to do much earlier this semester.
Oh yeah,
But I probably forgot it.
About the activities.
Right. And then look at that chart, and when you look at a chart, you should come up with your own, you know, the instructor, of course the instructor can tell you what the key take-home points from the chart is, but then do you remember that? No, I find that people never remember that. No matter how many times I say it, I could say it like 5 times, and people, but if you come up with your own personal, you know, key points, then it's much more memorable, isn't it? Because it's in your own words, which is a lot better than just repeating somebody else's words. I don't know if I want to do this. We don't have time.
Okay, if you don't have time, just move on. Just ask a problem or something.
Just give us a page.
Yeah, page 587. Yeah, let me do that because you look it up.
Can you go over the chapter 17 exam, number 15?
Yeah. I'll do that right after. I mean, how many people got this?
Yeah.
No? Okay. Let's take a look. 9.2 grams of sodium chloride, what is the molarity of the solute? And so you would have to review, you know, for this particular problem, you have to go back and look at this. And so it's just 9.2 grams of sodium chloride. Convert that into moles. So a mole of sodium chloride,
58.4428.
thanks, 442,
Yeah, grams.
8 grams. Thanks.
I thought the molarity was just that, and then,
That's the molarity of sodium chloride.
Now we gotta convert it over for the.
Wow.
but why do you need the other conversion?
Okay, then I need to go. I need to go back to chapter 13. Then let me just do that. It'll be quicker, maybe. Let me just see.
No, there's not much people here. But why they have to be that? I find there's no point.
All right. So what is this chart telling us? Table 13.3, page 587, chapter 13. If we look at sodium chloride, what are all these numbers saying? Just if somebody asks you, what's this table telling you? Telling me? What's this supposed to be telling you? Mm-hmm.
I found correlation that if the solute's molarity goes down as the solution gets more dilute. The molarity.
What's up?
Isn't it the ionic interactions in the solution? So you only have two, like, when you have infinite solution, you only have two ions in it.
Well, as you're approaching infinite dilution,
Yeah.
this is not two ions in the sense that you only have one sodium ion and one chloride ion. It's in a different sense. You're right, it's two ions, but how would you wouldn't say two ions? You would say,
Two species.
yeah. Sodium chloride is supposed to split up into a sodium ion and a chloride ion. That's why it's two. This is two solute particles. So for every one, this is 1 mole out. That's what it says. For every 1 mole of sodium chloride, how many species does it split up into? 2. It splits up into 1 mole of sodium ions and 1 mole of chloride ions.
So that's why.
And so this is the 2. This is splits up into 2 solute particles,
Which means
Per-
2 moles.
sodium chloride. 2 moles of solute particles, right? But at higher concentrations, what happens? Now, David, you can come in with that. Ion.
Yeah.
Right? It becomes less and less ideal, right? And so how do we deal with this? Well, I told you how we're going to deal with it. We're going to deal with it by ignoring it, and we're going to assume that everything's going to split up ideally. Even when we're doing the KSP equation, does it really split up ideally like that? How we wrote it? Well, looking at this, it doesn't look likely, especially if it's a higher charge. So for example, if we do PbCl2, you know, we do PbCl2, we assume it splits up into Pb2 plus and 2Cl minuses. Do you think it really does that? Well, it depends on the concentration. The concentration is going to be very small, and so maybe it'll get closer, but maybe not. You know, maybe there could be other, what we call ion pairs that form, and it could get more complicated. And this is something we'll see. If we want to deal with all this, then we need more. All of a sudden things get much more complex because there are a whole bunch of different equilibria that can happen. You know, ion pair equilibria followed by destruction of the ion pair followed by multiple ion pairing. You know, and so
That's Chem 1B stuff.
no, it's actually beyond Chem 1B stuff. So this stuff that's beyond Chem 1B, you know, how do you account for activities? We don't. Have we ever accounted for activities? No, we just assume that it's going to behave ideally. Now, if you have to account for activities, then you need to use some,
Equation or other factors.
you need to do some serious calculations, or you need to use some program like what?
Visual Mentor? Spartan?
Visual Mintech, right. When are we doing Visual Mintech? Is that this week or next week? Is it this week, Thursday? Is that when I had Visual Mintech planned? Or next week?
Next week.
Next week? Okay, thank you.
Or Thursday, I don't know. Because it's March 29 now.
All right.
Yeah, it shows for April 5th is what you got listed here.
All right, that's fine. Next week, that's good. Okay, the limiting values 2, 2, 3. These are, you know, the ideal values. You know, lead-2 nitrate should split up into 3 ions. Magnesium sulfate into 2. Are reached when the solution is infinitely dilute. Note that a solute whose ions are singly charged approaches its limiting value more quickly than does a solute whose ions carry higher charges.
Why?
Well, you can see here, sodium chloride splits up into 2, and magnesium sulfate splits up into 2, but look how different they are. You know, which one's more ideal, sodium chloride or magnesium sulfate? Sodium chloride is much more ideal, right? Magnesium sulfate is less ideal. Why? Higher charges means what? Stronger. Right, exactly, Scott. Right. Stronger ion-ion attractions. Not only this, but, you know, I don't know if you guys remember, but benzoic acid, you know, even though benzoic acid doesn't have any net charge, benzoic acid is notoriously bad because benzoic acid has very strong hydrogen bonding interactions. And benzoic acid deviates significantly from ideal behavior because the benzoic acid molecules like to line up with each other. No, I've got to twist this. And so they like to line up with each other and form, you know what these things are called? I mean, well, these are carboxylic acid. Benzoic acid is carboxylic acid. Oh, should I screw this up here? Oops, this is carbon. I have it inverted.
Oh, isotonic is the same concentration of solid particles. And we're trying to reach the concentration.
Benzoic acid is very bad because of this. This is called a dimer. And so if you have something like 1 molar benzoic acid, the actual molarity of the solute particles is a lot smaller because the benzoic acids molecules like this pair up like this. I remember this question very well because when I was at UCSB, this was one of the questions on the Chem. It was like the Chem 1A test.
Chem 1A?
Yeah. The question was, why does benzoic acid deviate so much from the predicted That was like boiling point elevation, or I forgot, freezing point, something like that.
It was like a stronger acid, that's not what we're talking.
No.
It's a stronger acid because the electrons can fit in.
Oh, yeah, that's a separate issue, yeah. There's gonna be, ion, yeah, right, benzoic acid, right, is stronger than you'd predict, considering it has a hydrocarbon group here. The hydrocarbon group is what we call an aromatic, which is gonna behave differently than the other types of hydrocarbon groups, which are the aliphatic. The aromatics have the p orbitals all lined up, and so you can have the electrons delocalized, pi bonding network. But that's a separate issue. This is talking about the number of solute particles. And so in line with that is this diagram here,
But
showing
on
these
five,
clusters.
but on
defined.
580, it doesn't, it just says the isotonic solution is this many grams. It just didn't say the moles, the solid.
I know, because it's just a matter of convenience. A matter of convenience. This has nothing to do with the chemistry. This is just all to do with what's the easiest way to make an isotonic saline solution. Take 9.2 grams of sodium chloride. This is like an engineering equation. Engineering equation, they don't want to see how it's derived. You know, they don't want all the math. They don't care about the theory. They just want an equation
Easy.
to punch in a number and not think about it. You know, this is like I asked when I was in charge of the science club here for a while, many years ago, and then I asked the Dow chemical plant, or it's not a Dow chemical, it's a Dow plant that used to be down on Crenshaw and then changed owners. Oh, we'd like to get a tour of your plant, right? They said, no, this is a bad plant to go to because none of us understand what's going on. All we do is we just come in, turn the key, and push the buttons. If anything goes wrong, we make a phone call and some guy comes immediately to fix everything. Right. And so they said, don't come here because we can't answer any questions. I thought that was funny. But that's the same thing like this. Don't ask me what's going on. All I know is I have to put 9.2 grams in this bottle and then fill it to this line with water. That's it. But this is not the chemistry that's going on, right? Uh-huh.
I know, but I still don't know why we gotta find the moles of solid particles.
Well, you know what you should do, Kelly? You should go back to this and read about colligative properties.
Okay.
Because the colligative properties are going to depend on the molarity of solute particles or the molality of solute particles. That's why we got to find out the moles. It depends on how many solute particles, not how many grams, but how many. Some particles are heavy, some particles are light, but it doesn't matter. Light particle versus a heavy particle, it's still counted as one particle. You know, and so and the reason is because of these types of attractions between ions and also between water molecules and ions. These are called ion dipole attractions. Ion dipole attractions can be significant. And so we need to know how many particles, because the colligative properties are going to depend on the number of particles. The more particles you have, the more like vapor pressure is lowered. Remember vapor pressure lowering? You know, there are different ways of thinking about vapor pressure lowering, but a pure liquid, let's say you have some solid particles here versus a solution. This is a solution, this is pure liquid. This is why it's good to review. It's always good to review because it's easy to forget this stuff, and if you forget it, then well, if you never use it again, then no big deal. You know, some people are saying get rid of algebra because you'll never use it again. For most people, right?
Oh no, we can use algebra.
Well, I just read this in the LA Times yesterday, but anyway, this, you know, which one's going to have a higher vapor pressure? Yeah. Which one's going to have a higher vapor pressure? Pure? Which one's going to evaporate more of these surface molecules into the gaseous state? Huh? The pure one or the solution?
Solution.
No. The higher vapor pressure, well, then maybe I don't, actually, I'm not going to spend it too much more time. Just don't worry about it. You need to know how many moles are inside there. And it has to do with, if you have more solute particles, what's gonna happen to the vapor pressure? It's gonna keep going down and down and down. And so just think about it this way. There's some reason we need to know the moles. And it has to do with the moles of particles themselves. And so if that's the reason, let's go ahead with that. And
Add another conversion.
Disassociate.
right, and so we're going to assume, this is where we make the assumption. We're going to assume that it dissociates into,
Na and Cl.
yes, so we get 2 moles of solute particles, 1 sodium and 1 chloride, for every 1 mole of sodium chloride. So 2 particles per, that's what it dissociates into. And so we're assuming it's behaving ideally, right?
Yeah, the book says to assume that, but I don't know where, where in the problem I can use this information. Like can I do a point?
If you need to figure out the molarity, do you have to figure out the moles? If you need to figure, yes, if you need to figure out the moles of particles, then this is undercounting.
I know, but the thing I'm trying to say is that okay, the problem's giving me assuming that NaCl completely dissociates, but I don't know where to use the information in the problem. I couldn't figure that out.
Okay, well, we'll talk, how about this? We'll discuss this later during the break, or the office.
Office hours.
Yeah, in between. Then we'll go back and look at chapter 13. We could do that together. But basically, when I look at this problem is 2 equation, 2 unknown setup. You have, it's not just the ratio, but you have one more constraint. What's the other constraint in addition to the ratio?
The concentration.
Right, well, it has to be isotonic, And so what we have to do is we have to come up with 2 equations, right? And a 2 unknown type deal. And so the other equation that's gonna pop up is this one, where once we figure out this is the moles of particles
0.3147.
per liter. This has to equal the same thing for the number of moles of particles, but it's H2PO4 minus. Well, there's only 1, right? But there's a problem here because it's not just H2PO4 minus. We're getting this from, what's it coming from? Well, it's coming from a solid salt. So what we have to do is we have to look at, what was it, potassium?
Potassium, dihydrogen phosphate, and then
Sodium
sodium.
monohydrogen.
Sodium phosphate.
Okay, and then, this has got to be the number of moles of particles of potassium ions, right? Plus the number of moles of particles of the monohydrogen phosphate. And the monohydrogen phosphate is coming from the sodium salt?
Yeah.
Yeah.
Okay, and so the number of moles of particles for the sodium. And so now all of a sudden we have too many unknowns, but we don't really have too many unknowns because the potassiums and the dihydrogen phosphate are related. For every potassium dihydrogen phosphate we have, we end up with 1 potassium and 1 dihydrogen phosphate. And so these are the same numbers. And for every sodium monohydrogen phosphate, and it's a hydrate, the hydrate though, does that impact the number of moles of particles? No, it's just water, so it's the same thing. And so this is going to be a 2-to-1 ratio here. And so this will be 2-to-1, this will be 1-to-1. And so what we can do is we can figure out the number of moles of potassium dihydrogen phosphate and the number of moles of sodium. And it has to be in what ratio?
1.6.
Yeah, it has to be in the 1.58 whatever ratio here. And so we have to do some extra calculation in order to figure it out. And so you just come up with additional constraints on the system. That's how you'd set it up.
Oh.
But you know, in my for my test, the one thing you'll note is I'm not going to test you on Chem 1A material. I figure a lot of people it's just long lost, long forgotten memory. It's good though to go back, but you know the primary thing is the Chem 1B. If you've forgotten the Chem 1A, well, okay, I can live with that. But the Chem 1B, you shouldn't. And so a problem like this, I wouldn't ask you. You know, this is just because, you know why I put this question in?
Why?
Because of activity. This chapter especially, there are deviations from ideal behavior that we might as well talk about it now.
And you don't have to. It's your choice.
No, I wanted to talk about deviations from ideal behavior because there's a couple of other effects. So for example, silver chloride. You know, silver chloride, let's talk about deviations from ideal behavior. Then I'll answer the other questions since we're on this topic right now. Deviations from ideal behavior. Silver chloride, when it dissolves in pure water, is going to form silver ions and chloride ions. And so the question is silver chloride, is it more soluble in, let's say, in pure water versus sodium nitrate solution? Which one is it more soluble in? Or is it the same solubility in both? It turns out that silver chloride is more soluble in sodium nitrate than in pure water. And the question comes up, why? Why would silver chloride be more soluble in sodium nitrate? And the reason is this. This is the reason why it's more soluble in, ion pairing. And so what happens is this. In pure water, this is it. This is the only equilibrium. But in sodium nitrate solution, what can happen is this. Even though the nitrates don't react, with silver ions, they can be taken out. By nitrate in this way. The nitrates surround the silvers. If the nitrates end up surrounding the silvers like this, they aren't bonding to the silver, they're just attracted to the silver ions. That means that, this is like a Le Chatelier's effect, where you're decreasing what we call the free silver ion. The free meaning it can easily, this should not be nitrate here, sorry, this should be chloride. All right. So this is what we call free, and this is what we call hindered. It's hindered because it's got all these other ions around it, so it can't really find a chloride to recrystallize or precipitate with, right? When that happens. And the same thing with the chloride. The chlorides will be surrounded with sodium ions, even though, yes, sodium chloride is not going to precipitate, but the chlorides aren't going to be as free as they once were, because if sodiums are kind of interfering with it, then
can't precipitate.
Right, and so this is what happens, especially at higher concentrations. This kind of stuff can happen. And therefore, we get something called it's not a huge effect. This is called the uncommon ion effect.
Uncommon ion effect.
Uncommon ion effect. And we can see what kind of impact the uncommon ion effect results in by looking at this chart here, chapter 18.
That question 93 that you gave us, that's really interesting.
We'll take a look at All right, the uncommon ion effect, aka the salt effect. This shows the solubility of silver chromate. The silver chromate in pure water has some fixed solubility, but which is here. And so this is just the solubility in pure water. Okay, if we add potassium nitrate, then the solubility actually increases due to ion pairing interactions like this. Right? And so we see an increase. It's not huge. Versus this would be the common ion effect. For example, what are we adding here? Chromate or silver?
Chromate.
Chromate? Yeah, okay, we're adding chromate. And so as we add chromate, the solubility just drops dramatically. This is called precipitation. You want to precipitate, just add some more precipitation into chromate.
But silver chromate already precipitated.
I know, but we can precipitate more by adding more chromate. We can precipitate more of the silver ion. More chromate.
It's gonna be a red, rusty, grapefruity.
Oh no, silver chromate's not red. Rust. A lot of them are yellow. Okay. Let's see. At least I think. Let me think. Can't remember actually. All right, so that's an uncommon ion effect. Whatever it's called, the diverse non-common ion effect, aka the salt effect, the uncommon ion effect. Another thing that impacts our calculations is this. We call this incomplete dissociation or ion pair formation. Here. And so magnesium fluoride should dissociate into one magnesium and two fluorides, but the first fluoride breaks off, the second one kind of gets stuck. You get this. And so we end up with this species. It's the MgF plus 1 pair. And so MgF plus 1. Are we accounting for the there it is, MgF plus 1. Are we accounting for this ion pair in our calculations? No. We're not accounting for any incomplete. We're just assuming ideal behavior. And so if we assume ideal behavior, is that entirely correct? No. And so what impact does that make on our calculation? Our calculation is going to be wrong, right?
Yes.
You know, if we were to account for this, I told you the calculations are going to get quite horrendous. And so let's just look at this, PBI2. All we're doing is what's in black here. You see that? When we do this calculation, we just say, okay, PBI2 splits up into PB2 plus and 2 iodides. Fine. But really, there's a lot going on here because what we have is we have this. This is a solid lattice, ionic lattice. And so what we can have are ion pairs. This would be an ion pair where the first iodide breaks off, but the second one doesn't completely. This would be another one. This species here is like a PBI2 molecule in the water, but all it is a dual ion pair. You got the PB2 plus and an iodide stuck here and an iodide stuck here, and this thing's in solution. You know, it's got mobility. And then we have this, because it turns out that PBI2 is, we can actually form complexes of this. And so if we have enough iodide, we can form this triiodoplumebate ion, and we can also go up to the tetraiodoplumbate ion. And so are we accounting for all these other? No, because all of a sudden the calculation is going to be, you have to do this, you have to solve this, what? Simultaneous. How many equilibria is that? That's horrendous, right? That's a horrendous calculation. And so what we're doing is we're ignoring it. But you know what? Even though this is a horrendous calculation, it's super easy if you're using Visual Mintech. We could do this, no problem, Visual Mintech, because you don't do anything. You just hit the button and set up some initial parameters. It's so easy to use, and then it does the calculation for you. But, that's, we want to know a little bit more, because how does Visual Mentech come up with these calculations? Well, they use the latest activities and other things like that. And so what we got to do is we got to assess the limitations of the KSP. Well, when we assess it, it's different. It's different if somebody tells you something, you know, oh, it's close, you know, but off, right? Versus if you actually see it. What you're going to do is you're going to do the calculation by hand, and then you're going to do the calculation using Visual Mentech. Maybe we'll do PBI2, and then you'll see what % differences you have. What species are you missing? And so we'll get a better assessment. But the assessment here is this. Basically, we'll summarize it. Here. So they're talking about some limitations for calcium sulfate. But if we are within a factor of 10 or even 100, then the calculation was a success. But you know, a factor of 10 or 100, is that good? Is that highly accurate? No, and then the higher the charges go, right, and the higher the concentrations of those species are, the even farther off we are going to be in our calculations. So in one sense, I wanted to bring this, I assigned this problem, even though it's all Chem 1A, a lot of it, because a couple of things. One, it has multiple equations, so you got to solve a system of equations, right, which we've done. And you don't get that many system of equations in general chem, so it's nice to have those when they pop up. And then that is a very practical problem, because you know somebody might ask you to make a buffer that's isotonic. Well, how would you make it? And so it's a very practical problem. And two, it gets you thinking back, you know, about all this stuff. You know, and this is where we talk in this particular chapter about, you know, so far we've been assuming everything behaves ideally. Has that been a great assumption? Well, you know, I guess you know, a factor of 10 or a factor of 100, that's okay, you know, but maybe not the best. If you want more accurate results, then probably best is to do some computational, rather than just by hand, assuming ideal behavior. But you know, some of the calculations are going to be great because the solutions behave fairly ideal anyway. You know? And so we look at it case by case. It's like the ideal gas law, right? When you do an ideal gas law calculation of helium versus xenon, are you going to get equally accurate results? Helium versus xenon? No, which one would give you more accurate results?
Helium.
Helium is going to give you much more accurate results because helium behaves much more ideally than xenon, right? And so if you do an ideal gas law equation on helium versus xenon, I don't trust the two equally, right? Well, same thing here. You know, if you're calculating different things, you know, things that are going to help you are low concentration, that is very low KSP, and kind of low charges. That'll help you. All right. So I kind of skipped this section earlier because I was waiting to talk about it a little later, but now's a good time to talk about it.
So is number 70 really a hard problem?
Number what?
70.
Number 70, you're making it harder because the colligative properties is a little fuzzy. But if you go back and you review the colligative properties, then it's it's hard because it's multiple equations, but it's not that hard because, you know, you just got to understand the molarities.
Okay, this is a final reflection. Can I press the new button?
I mean, we could set it up. That was one way of setting up. There are other ways of setting that up, but you got to know how it splits, you know. So, for example, if we assume ideal behavior, then the potassium dihydrogen phosphate splits up into 2 particles, and the sodium monohydrogen phosphate splits up into 3 particles. And so, then you could simplify that and condense it, you know, for the particles. Okay, and they have to occur in that ratio, so you got to do that ratio too. And so it's complicated. I just started it, you know, just putting some ideas on the board, but it's much more. You got to do much more. All right, let's talk about what was the other question you had on the from the practice test?
Number 16.
Number 16. Can you just read out the?
Calculate the pH when 1 drop of 6 molar HCl is added to 200 milliliters of buffer containing 1 molar HCl, and then the Ka is 7.54, and then 0.38 molar of OCl minus.
Whoa.
Is this it? Something like this?
0.288 molar of.
288.
Yep.
So we have this buffer. We want the pH change?
You just calculate the pH
The pH?
when 1 drop of 6 molar HCl is added.
Alright, what's the pH of this buffer? Can you figure it out?
You use the hand Hasselbalch.
Yeah, you use that. What was the pKa?
Well, it just says Ka.
Oh, the Ka? So we'll have to take the negative log of that. 7.5?
4.
4.
That's it.
7.54 is the Ka?
That's what it says on the. Yes, it says Ka equals 7.54.
That's wrong, sorry. I should fix that. I must have forgotten to write the rest of that. Yeah. HOCl is called hypochlorous acid. Hypochlorous acid, the Ka is not so big. I don't know if it's on that chart.
It's not possibly PKA or.
Yeah, that could be the pKa.
Or does that doesn't sound like the.
KA.
Yeah, 7.54 could be the pKa.
Yeah, it's PK.
Okay, sorry.
Okay.
Yeah. So I must screwed that up. So
You
it's
want
seven.
the KA as long as
No, I don't want the Ka. Just I'm curious what the initial pH is. Starting off at.
$6.999.
6.999, so about 7. 7.00.
Why would I have a new?
6.999, is there one more digit? We're actually allowed 3. 3?
99939.
Okay, thank you. Close to 7. Then we add 1 drop of HCl,
Yes.
and what's the volume of this buffer?
200 milliliters.
200 milliliters.
we got another 0.05 liters for.
Yeah, we'll do 0.05 liters for that. So
I meant milliliters.
Hmm?
I meant milliliters, not liters.
yeah, 0.05 milliliters.
0.05 liters is huge.
And so what do we do in a problem like this? Well, if you're ever unsure what to do, you do the solution dilution first and go on from there. This pad's okay. And so we're gonna be left with 200.05 milliliters. Then we gotta figure out the new concentrations. What's the molarity of the HCl?
6.
And so we need to figure out the new HCl concentration, 0.05 over 200, 0.05 dilution.
That's a significant dilution.
Yeah, that's a huge dilution. Which is,
We got 0.001499.
0.001499.
Yeah.
That's really dilute.
Yeah. Well, it's a huge dilution, so.
Where's it going?
He said it's like
just get a pen. The OCl minus is gonna be,
CL minus is,
wait, actually, let's do HOCl since we're doing.
it's 100 milliliters divided by 200.05.
Yeah, this is not a big dilution, but we'll do the calculation nonetheless. 200 to 200.5, 1.00 molar.
Professor, how much are we assuming the drop is?
0.05 milliliters.
105.
Yeah,
Wait, oh,
that's what we're assuming. It's not exactly
That was
0.05.
0.5.
Hmm?
That was 0.5.
No, this is even,
0.5 is 2 drops per milliliter.
that's a half a milliliter.
Yeah.
Drop. Big drop.
That's a big drop, yeah.
Are we supposed to know how much drop is? Or?
Yeah.
From Chem 1 a penny lab.
From Chem 4, you did the drops. Do you remember that?
I did Chem 1 a penny lab.
And the Chem 1A is the penny lab, but there's that thing. I don't know if I skipped it. I might have skipped it.
we did the penny lab.
Just yet, it's 0.05 milliliters a drop.
But in qualitative analysis, I might have mentioned it, might not. It depends on the surface tension. If the surface tension is weak, right?
Like as of mercury?
If the surface tension is weak, then you need a lot of drops. If the surface tension is strong, then you need fewer drops.
How about mercury, a solution of mercury? Liquid mercury.
Well, we aren't going to get any drops of liquid. We're going to talk about aqueous solutions, water solutions right now, not mercury, liquid. Yeah, the aqueous solution, so it ranges. So if you look at something like 6 molar ammonia, where the surface tension is very weak, then it's more like 30 drops per milliliter, not 20. And so this is just a total guess. You know, but based on years and years of Chem 1A and Chem 4, most people would get around 0.048 or so milliliters per drop.
Experiment?
So it's close enough to 0.05.
Professor, I think
Yeah.
on 16 it says 0.28 grams GM. It's like a little GM. Is that it? Or,
What is that?
oh,
Grams per mole.
well, it's still.
Isn't that a?
What does that symbol? Okay, sorry.
All right, so what does this concentration amount to?
0.9998.
Then the OCl minus is the same dilution factor.
How come?
I think it's 0.28.
Yeah, times point
How come
two.
it's the same dilution factor?
Because it's in this solution here. Both of these are in this solution. Right
Of the 200.
So 0.2879.
here. So it barely changed. This is about 1, this is about 280. All right, what's the next step? This is chapter 17 stuff. Chapter 17 deals with these mixtures. So the steps are always the same, no matter what you do. You take the strongest acid, which is going to be HCl, and the strongest base, OCl minus. Figure it out. So HCl, this is going to make Cl minus plus HOCl.
Professor, is it 200 over 200.05
Yes,
multiplied by 2.8?
0.280.
Yeah, it should be 0.2. Yeah, okay. Right.
Yeah.
0.287.
So this, we just plug in the numbers here, 1499 molar, OCl minus 0.2879 molar. Cl minus is not going to change the pH, is it? No. But the Cl minus will plug it in here anyway. This is going to come out to 0. And then the HOCl, well, we have HCl 0.9998 molar. Those are our initials. What is K for this equation? K for the reaction?
Strong.
It's going to be very,
Very.
very large. And so what's the limiting reagent?
HCl.
The HCl goes to 0. We gotta lose 0.001499, and then we gain that over here, 0.001499 here. Figure it out.
0.2864.
0.2864.
We have quite a lot of hypochlorite.
And then the HOCl.
1.001.
All right. Now we take the strongest acid and the strongest base of what remains. Well, the strongest acid is HOCl. The strongest base is OCl minus. So HOCl plus OCl minus yields the same thing, right? Because they're conjugates of each other. And so you might recognize this mixture. This is a mixture of weak acid and a weak base. They're conjugates. In other words, this is a Henderson-Hasselbalch buffer, which means that the pH is equal to
PK plus.
7.54 plus the log of the base, which is, a lot of people, they don't care what the base is. You know, every year on a test, people will write any base in here, like sodium hydroxide, and any acid in here, like HCl, but that's not the case. They have to be conjugates, and they have to be both be weak. They can't, one can't be strong and the other weak. What do you get? 6.9? 998. Did the pH change much? We're going from 69993 to 69998. No. And so the buffer did its job. If their calculation is correct.
Why does the pH increase if you're adding acid?
Oh, that's a good question. The pH.
It did
So,
from 6.999 to
Ah, I noticed that.
Yeah,
Oh.
it's 6.5.
I noticed that.
All right. I must have made a mistake. You can't. You're right.
It went down.
That would have been a check. The pH has to go down if we're adding strong acid.
6.999 to 6.996.
Okay. All right. Thanks. 6.996.
But it's still increasing.
No, it went down from 9.3 to 6.
Okay.
Although, you know, it's still pretty close, because if we were to round this.
so if you do it with millimoles, you get a different answer. So you get like 9.8417. Would you,
9.847?
It's confusing because in the book they use the milligram method and then like stoichiometry, and then we learn it like.
would you take a millimole too, or do you want it like? is it-
No, with millimoles, this gives us the exact same.
It should.
In fact, let's do, you want to, well, I don't know if you
I
want
want
to
to
do
do a
it.
minimal. I don't want to do solution. I don't want to.
You want to do it with millimoles?
Yes, I want to do a minimal.
All right. All right.
Give us an example of millimole and give us an example of solution.
Okay, if I do it with millimoles, can I jump to this equation? This is the book's equation that they do.
Oh, that's even more
Is that-
confusing.
Are you good up to here? This is the book's, right? The book uses this equation, or do they not use this equation?
Is that a minus?
Minus.
That looks weird.
Yeah, but it's bitter.
They pretty much figure out the initial millimoles.
Do they do the ice table in the book?
Yeah.
Yeah,
All right.
pretty much.
All right, this is after the ice table. In fact, this is just taking the ice table and doing this.
Yeah, I use millimoles in our table.
All right. Do you see this comes from the ice table here?
Yeah.
The reason it comes from the ice table is this. You get the millimoles of HCl. You get the millimoles of OCl minus and the millimoles of HOCl. And then the limiting reagent is
The HCl.
the HCl. So this is minus millimoles of HCl, minus millimoles of HCl. Actually, this is wrong. We need to convert this to millimoles, sorry. Millimoles of B. This is gonna be millimoles of A. And so what we end up with is millimoles of OCl minus millimoles of the HCl. And so that's our base here, millimoles of base of minus millimoles of HCl. And then the acid is millimoles of HOCl plus millimoles of HCl, because HCl is the limiting reagent. And so this is where this equation from the book comes from that they use quite often. But it's the same thing. The thing about using millimoles for buffers is that the volume cancels out, because the acid and base are in the same volumes, the liters cancel out here. And so you could use that if you're in the buffer region. You could also use this if you're in the equivalence point for a amphoteric. But you cannot use this if you're outside the buffer region. From my experience, and you could use whatever way you want. I really don't care. If you want to use millimoles, that's fine. But I don't talk about millimoles, because the more things and the more ways I solve these problems, actually, maybe that's not accurate. The more time it takes. So I don't want to spend too much time talking about it, even though it's useful to know multiple ways of solving this. I just stick with one method, that is solution dilution, followed by this, followed by that, because it works for every single problem on the titration curve. Right.
But what if we do the solution dilution where the X milliliters is not known? It's gonna make things more confusing.
No, it doesn't, because you just have two equations, two unknowns. That's that kind of thing. That's it. You just consolidate. We did it. We didn't call it X milliliters. We called it Z milliliters, and we did a bunch of them. It wasn't that hard. Well, how would you do that? Now, how would you do this backwards using millimole method? Well, I've done that too. Going backwards using the millimole method, you have to come up with another equation that shows how many milliliters you need to add, right, to get that to that particular point. It's okay in the buffer region, because you just say, forget that, I'm just going to use a shortcut, right? But if you wanted to do it in the buffer region, how would you do it to solve for Z milliliters, right? Also, if you're past the buffer region and you're using millimoles, then how would you do it? It's doable. It's not that hard. It's just, not that easy. Not as easy as just doing the same way for each problem. Okay.
But we do end up with millimoles in the test.
I don't care.
No?
No. I don't care at all. Whatever your preference is good. Okay, other questions?
I just had one, on the Henderson-Hasselbeck buffer, we were using the ratio of 200 milliliters to 200.05 on that.
Mm-hmm.
How come, isn't the species of like HCl like 100 milliliters for the 200.05 and then 100 milliliters for the OCl also? It's not, why is it 200?
Yeah, how many, was it one drop of HCl?
Yeah, no, it's just like this, like, on these concentrations here. How come they're not 100 each when we added 100 milliliters of each one? Instead of 200, isn't that considered as OCl and HOCl together?
No, because then I don't know, I must have made a mistake, because was this buffer made from 100 and 100?
It was made from, 100, oh no, it doesn't, I'm sorry, it says 200 milliliters of buffer.
All right.
Sorry, that's where it is, I got it.
If I asked you 100 plus 100, then you would have had to do that.
Yeah, okay, that's where I got
Okay,
confused.
all right.
That's normally how they ask it in the rest of the questions.
Yeah, well, you have to be prepared. You have to be prepared for both solution dilution and no solution dilution.
Gotcha.
Okay. All right, any other questions on this? No? Okay. All right, let's move on to,
Okay.
move back to chapter 18 here. What were we talking about? We're talking about KSP double dagger.
Yes,
Yeah.
you're about to tell us all about it.
We did a calculation, didn't we calculate the solubility? Or set it up at least?
Oh crap, we're almost out of time.
That's all right.
We still have more time. Did we talk about KSP, did we do a solubility calculation with KSP double dagger?
No.
No. Did we talk about KSP double dagger?
You mentioned it. You said, that there's a chart. Oh, that's what, you use appendix B to find it.
double dagger, you did KSPA double dagger.
Okay, KSPA. All right, KSP double dagger is different because KSP double dagger, for every S, you have to add an H2O liquid. Why? Because somebody explain why we have to add an H2O liquid for every sulfur.
So sulfides are too strong of a base to carbonate with.
Yeah, they'll attack water completely. And so this is going to form Cu2 plus HS minus plus OH minus. So does everybody see how that equation was derived? It's from adding the two equations. Sulfide's going to attack water. So we talked about this. Now we talk about KSPA, we could vary the hydroxide. That'll tell us it, but hydroxide is not the only base here. There's another base here. What is it?
Yes.
HS minus. And so, figuring out the pH sensitivity of this, well, HS minus is a pretty decent base in terms of strength. And so if we want KSP double dagger and we want the pH dependence, then we'll call it the KSPA double dagger. Because the KSPA double dagger is you just add acid. Now, acid's going to attack the hydroxide for sure. Acid attacks the hydroxide, we're left with H2O liquid plus H2O liquid. You should recognize this equation because it's just the reverse of KW. So this is going to be called KSP double dagger. This is KW, but since it's the reverse, we have to invert it. And then, well, that's not the only base acid can attack. The other base is HS minus.
But why? But why the two H2O liquids, not just one? One's in narrow?
It has to be balanced. Otherwise, if it's just one,
It's H4O2.
we're missing two hydrogens and we're missing one oxygen.
Okay, I get it.
Okay, and then this is going to form H2S and H2O. Again, this is the balance. When you look at this one, even though, for both of these, we would say, K, what's K for this reaction? K for this reaction is very, very, very large. But we aren't going to use very, very, very large for this. We're actually going to come up with a value for this. Now, the value isn't so very, very, very large. The value is 10 to the positive 14. That's not so huge, is that? And so why am I calling it very, 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 very large? The reason is the way we do these problems. The whole idea behind very large, very, very large, and very, very, very large is to reset the equilibrium. When you do very large, you're saying, okay, 100% forward reaction, and then you let things equilibrate in reverse. And so it's just a method for solving these problems. It's called resetting, but they don't call it resetting, right? And then if you notice, what we do after the very large steps is we figure out all the equilibria via ice tables. You see that?
Yes.
And so this is a way to, reset it without calling it resetting, okay? But essentially that's what we're doing. And so we aren't gonna, we could call this very, very, very large, but then we gotta do more calculations. So what we're gonna do is, since this works for the combined method, we don't have to do this resetting stuff. We're just gonna combine it. And so you have to note that. You have to make a mental note, because this one in the forward direction we call not very, very, very large. We call this one very, very large, right? Strong acid, weak base. So we call it very, very large. Oh. But here, look at the reverse. What is the reverse?
Very, very small.
No, the reverse is what we call the Ka of H2S. Well, this is going to be 1 over the Ka of H2S. The Ka of H2S is 1.0 times 10 to the negative 7. That means this is 1.0 times 10 to the positive 7, you know? It's not such a huge number. We can deal with that number, right? And so why weren't we dealing with it earlier? Well, the reason we weren't dealing with it earlier is because it makes the calculations a lot easier if you just reset it using very large and very, very, very large and very, very large, right? But in this chapter, we aren't going to do that. In this chapter, we're going to get the numbers, and then we're going to do very easy method. The very easy method is to combine. And so we're going to combine this. We're going to CuS solid. And why does the combine work?
All species are accounted for.
No, not exactly. Why does the combine work?
Something about the speech.
Because it's simple.
No. Well, the combined works just the same reason it worked for the other ones. This is very small. What species are missing in our final equilibrium? We're missing some species. What species are we missing? OH minus and HS minus. And so in the combined, we're assuming that all the sulfide ends up as H2S. None of it ends up as HS minus. And all the oxygen is going to end up in water rather than any in hydroxide, right?
Yeah.
Is that an okay assumption? To completely ignore those species? Well, it's not 100% accurate, but it should be okay, because the first step is, this is a repeat of what I said. I think I said it twice before. The first step is
Very large.
very small, which means that we're going to generate very little. And the second two steps are very large, which means any bit we generate is going to be quickly consumed. And therefore, we don't expect much HS minus and OH minus, therefore we're going to ignore them.
Ah, I get it.
That's why the combined works. It doesn't work for everything, but it works in chapter 18 because of this particular behavior.
You don't generate too much what?
Hmm?
You don't generate too much what, so you pick H.
We don't generate much HS minus and OH minus.
Oh.
And what little we do generate is quickly captured and consumed. Therefore, the equilibrium concentrations of HS minus and OH minus should be very, very small. Therefore, we're going to completely ignore them. Otherwise, there's a mass balance problem here. This is called a mass balance problem because all the sulfur ends up in H2S. Therefore, there's no sulfur for HS minus, and all the oxygen ends up in water. There's no oxygen left over for OH minus. This is a mass balance problem. What we call a mass balance. Visual Mintac works at solving these equilibria using mass balance to make sure all the atoms are accounted for. Right. So we could do calculations, for example, of what pH. You know, the only thing is when we do the ice table, we got to figure out, is that the initial pH or is it constant pH, or, you know, is the hydronium initial or final, you know? And so we waters, so we just fill out the tables here. Then we could calculate the solubility. Some initial. The solubility, we just assumed that these are 0, right? Plus S, etc. Okay, that's KSP double dagger. There's another case where the combined method works quite effectively. And like hydronium, strong acid loves to react with bases, right? You know, the other scenario is we can take out not just the bases, but we can take out other ions as well using, in fact, this copper here. So I'm looking for things that attack this because essentially it's Le Chatelier's principle in action. So another way to get copper sulfide to dissolve is to attack it not with acid, but to attack it with, let's see what types of things I could attack it with ammonia.
Ammonia?
Mm-hmm. What would ammonia do?
Complex it.
Yes. I could attack it with ammonia. What else could I attack it with? Well, I'd go back here and look.
Hydroxide.
Well, hydroxide would decrease the solubility. Why would hydroxide decrease the solubility? Le Chatelier's principle. I want to increase the solubility. Let's say I want to dissolve this. And so what are the things I can do to increase it? Well, I can change the pH. I could add a complexing agent. And so one complexing agent would be ammonia. What would others be? And so I'd go to Appendix D and look. I could use ethylene diamine. I could use oxalato. I could use EDTA.
EDTA?
I could use
Wow,
cyanide.
I don't know EDTA was a complexing agent for copper. What would it form?
What would it form?
Yes.
It formed this.
What color it is? Wow.
This is this. The charge of this is copper 2. This is -4.
2 minutes.
Yes. That's what it formed. It looks like it all. No, EDTA complexes look pretty much everything. So let's take a look. I'm just looking at Appendix D, and so let's take a look at what other things it complexes with. So, well, actually, didn't save time here. I'm not going to bring this up. It looks like probably the most effective complexing agent is with cyanide to form the tetracyano complex of copper. And so there's one way to take out copper easily, and that's to complex it with 4-cyanide. And this would form this, the tetracyano, 2-. This is called K, what? What is this called? K. This is what I talked on the first day. Talked about this. This is called KF. This decent pen. KF for this is 2.0 times 10 to the 30th.
That's wow.
It's an enormous value. It's an enormous value.
Great complexing agent.
Yeah, it's a great complexing agent. And so cyanide loves copper too.
And iron too.
And so let's first talk about complexing agents here first. And so let's do a little side. But basically, this is not a side, but we'll look at KF. Basically, we could do it this way. One way we could get copper to dissolve easily is to add cyanide. And so we have CuS plus H2O liquid plus 4 cyanides is gonna give us CuCN 4 2 minus plus HS minus plus OH minus. K, for this is gonna be called KSPF. And since it's a double dagger, this would be KSPF double dagger. This is just KSP double dagger divided by KF. It doesn't have to be a double dagger KSP, we could just use it on anything. But this is a way to get things to dissolve. For example, like silver chloride, how could you dissolve silver chloride? Well, you add ammonia, because the ammonia will take out the silver ion, do a Le Chatelier's shift. So it's just a Le Chatelier's type shift here. And so let's look at KF first, because the KF, there's certain concepts about the KF. We call the copper 2 the free ion. And so this is going to be plus 4 cyanide. This is going to yield the CuCN for 2 minus. The CuCN for 2 minus, this is called the complex ion. And the total copper is the free plus the complex. Well, it turns out that at equilibrium, the free is very small. And so let's do a sample calculation here. Let's say I start off with 0.100 molar copper 2 plus ion, and then I'm going to add some cyanide, 1 molarity cyanide. Let's say I'm going to add 1.00 molar cyanide to this. And so I'm going to have a mixture. No solution dilution here. We'll just start off with these concentrations. 0.100 molar copper 2. And then 1.00 molar cyanide and 0 molar complex. So right now it's all free ion. And then what we're going to calculate is how much free and how much complex copper I have at equilibrium. And so I'm going to start this. But I'll tell you, there's going to be a problem right now. What's my problem right now?
Oh.
You're gonna have to reset.
I'm going to have to reset this. You see? This problem is actually impossible to solve without resetting, because the large K and calculator round off. The calculator's going to have a hard time.
It's gonna give you.
Especially, look at the KF value. I mean, it's huge. And so what we do is reset this. So if we reset this, it's going to come out to 0 molar. And what's this one going to come out to? Well, we're out of time. This comes out to 0.60 molar, and this one will come out to 0.100 molar. Right? And then we can solve it. Okay. All right, I'll stop here, and then we'll continue this next time.
Pretty interesting.